Today's topic is about ideal gases and non-ideal gases. Ideal gases obeys the ideal gas equation, that is PV is equal to nRT. It also obeys the postulates of kinetic molecular theory of a gases at all temperature and the pressure, especially the two postulates that are that there is no attraction or the repulsion between the gas molecules and the actual volume of the gas molecules are negligible as compared to the total volume of the container. Let's discuss a little bit detail about the ideal gases. Remember that ideal gases obeys the postulates of the kinetic molecular theory of the gases at all temperature and the pressure. These postulates are: number 1, that there is no force of attraction present between the gas molecules; number 2, that the actual volume of the gas molecule is negligible as compared to the total volume of the gas container. Actually, ideal gases can't exist in nature. These gases can obey these two assumptions of the kinetic molecular theory of the gases at high temperature and the low pressure, and they behave ideally. Let's discuss it in a little bit detail. Gases behave ideally only at high temperature and the low pressure, because at high temperature and the low pressure, the average kinetic energy of the gas molecules increases. And we know that according to the kinetic molecular theory of the gases, that the temperature is directly proportional to the kinetic energy. So when we increase the temperature, the kinetic energy of the molecules also increases. So the gas molecules move faster, and as a result, they move far apart from each other and create a large empty spaces between them. As we know that the size of the gas molecules are very small with large empty spaces between them. Therefore, there is no attractive forces present between these molecules at high temperature and the low pressure. Let's talk about the volume of the gas molecules. According to the kinetic molecular theory of the gases, the actual volume of the gas molecules is negligible as compared to the total volume of the gas container. We know that the gas molecules are very small and the container of the gas molecule is very big as compared to it. Just like a particle of a sand in front of a huge mountain. Therefore, we neglect the volume of the gas at high temperature and the low pressure. To understand the ideal gases more clearly, let's take an example. As you can see here in a diagram that I have a huge drum full of water and I add a few salt particles in it. So what happened next? Should it become saltish or not? Absolutely not. Because the salt particles are very small as compared to the size of the drum, and they are very few in number. Similarly, in case of the ideal gases, the gas molecules are very small. They occupy a very small space in a container. Therefore, we ignore the volume of a gas, and they are far apart from each other. Therefore, between the gas molecules, there is no attractive or the repulsive forces present between them at high temperature and the low pressure. And we ignore the actual volume of a gas as compared to the container of a gas. Volume. Non-ideal or rare gases. Rare gases don't obey the ideal gas equation, that is PV is equal to nRT, and the postulates of the kinetic molecular theory of a gases at all temperature and the pressure. So the deviation from the ideal behavior is due to low temperature and the high pressure. The gases deviate from the ideal behavior at a low temperature and the high pressure, because at the low temperature and the high pressure, the average kinetic energy of the molecules is low. Empty spaces among the molecules are very small and the molecules are come close to one another. So as a result, the gas molecules do possess the weak attractive forces that are called van der Waals forces and have a volume that can't be ignored as compared to the total volume of the gas container. Thus the deviation is more and the gases behave non-ideally at low temperature and the high pressure.